So broadly this talk is from a little bit different angle, trying to see what are the challenges in designing, like taking our RDMA-based designs for, especially for big data. We'll be talking both from the Hadoop side as well as from the Memcached side. So as most of us know, like these days there is a lot of discussion about big data. All kinds of people are talking. The rate of information growth appears to be exceeding the Moore's law. The amount of data is exploding. This is a May 2010 article. It said like 35 zettabytes of data will be generated and consumed by the end of this decade. So that is the kind of scale people are talking here. Now, if we take a look at especially the high performance networking and scientific computing, we heard a lot about MPI, parallel file systems, storage systems. So since InfiniBand was introduced in October 2000, almost like we have crossed 12.5 years. Okay, so a lot of significant developments have taken place, and all these systems are currently being deployed using the InfiniBand and the RDMA. And yesterday we talked about like some of the newer programming models like the PGAS, UPC, OpenSMEM, hybrid, etc. Okay. But then if you take a look at the big data or enterprise or commercial computing side, even though like they're focusing on the large data and data analysis, primarily like the Hadoop is one of the common environment which is being used. It is getting a lot of momentum, and also Memcached is also used in the Web 2.0. So the question here broadly is that can high performance interconnects benefit this kind of environment? Okay, so that is the goal here. And most of these systems currently, if you take a look, they still use 1 gigabit Ethernet. Okay, and of course there are concerns for performance and scalability, but the usage of high performance network is beginning to draw some interest. We are seeing a lot of different kinds of products coming out. Oracle, IBM, Google, all are working in these directions. Every few days you see Hadoop accelerator from many organizations. Okay, so those are the kind of things which are being pushed. So the question is, what are the challenges? And then where do the bottlenecks lie? And then can all these bottlenecks be alleviated using the types of designs we have done for scientific computing? Okay, so that was the broad challenge we at OSU started asking almost like 2.5 years back, just from a research perspective, trying to understand where are the issues, how these can be resolved. And so I'll try to share some of our findings and where we are. Okay, so I'll try to, those of you who are not, how many of you are familiar with Hadoop architecture? Okay, quite a few. So I'll just very quickly go over that, and then talk about some of the detailed challenges, and I'll spend a lot of time here like how we want to do an RDMA-based designs for all these different components and what kind of performance numbers we get with these designs, and then I'll conclude. Okay, so this is the typical like the Hadoop architecture. Many of you know like the 3 fundamental components here. The HDFS, which is the Hadoop distributed file system, is here. Then we have the MapReduce, and then the HBase, and of course there are all other type of components. And obviously this model has been designed to scale, but there is always like there is a high amount of communication during intermediate phases. So if you take a detailed look and then zoom in, so this is how the HDFS architecture looks like. So we have all different kinds of like name node which stores the file system namespace. There are data nodes, stores the data block, and then the whole environment actually is developed in Java. So that is one way, it's for portability, but as many of you know, Java doesn't go well with performance. Okay, so that is the kind of challenge we face. We can do the portable design, but performance will be the issue. And at a higher level, we can abstract this to this diagram to focus on the communication. So basically, we can say that these are the HDFS clients, and then these are the HDFS data nodes, and they are talking with high performance networks. So that's what we want to achieve. And for the time being, like all the HDFS or anything Apache Hadoop, if you download, they are designed with sockets. Okay? And now if you see another component here, which is the HBase, so that is the kind of like the database component of the Hadoop. Again, it has been an integral part of many data center applications. So broadly it looks like this. There's a HBase client here, there's a HBase master, there are some region servers, and they are connected with HDFS. So HDFS is there, HBase is running on top of that. Now from a communication perspective, here we'll see like a 2 tiers. So that means HBase clients are there, they are talking with HBase region servers, and then from the HBase region servers we are communicating with the HDFS. So there are 2 levels of communications which are going here. So then the other one, which is the Memcached architecture. So this comes from the Web 2.0 world. So here the idea is that we have any kind of a multi-tier data center architecture. So what we want to do is like trying to support a distributed caching layer. So that means we take memory from each of these nodes, like from here, let's say these nodes or from these nodes, and allows to aggregate spare memory from multiple nodes. So if I have a 16 nodes and I have like let's say 8 gigabytes of memory, I can aggregate and I have 128 gigabytes of memory. And what do we do with that? We can actually use it to cache database queries, results of API calls. So if similar kind of queries are coming again and again, I don't have to really go to the end file systems or database. These are like the hot data or the results from the hot queries are already available in the memory. So I should be able to very quickly read and send it out. So that's how to accelerate. Again, it is a scalable model. But now if you see this architecture, when I'm talking like taking memory from all these things, I'm trying to provide some kind of an aggregated memory. And then the data and the requests and responses might be moving around. And how can we accelerate that? Okay. So with a brief introduction here, so now if we take a look at this, the challenges. So currently what is happening is, if you see here, like we have a let's say 110 gig network here, then we have the sockets, and then this is the application. So that's the current design. And then there are different kinds of solutions being proposed. It's called accelerated sockets, like some parts are being accelerated. Okay. So if you take this approach, sockets are not designed for high performance, and especially the stream semantics. There are some often mismatch for the upper layers. Zero copy is not available for the non-blocking sockets. So we ask the question here that if we take like the Horse interface, which we have been talking here for Infiniment or iWarp or Rocky, any of these, can we actually take and do the design here? That means let's say this is an HDFS. Can we directly HDFS can run over IB? Or if it is a MapReduce, can it run over IB or HBase? So all these components, if they can run over IB, so that's the kind of the best performance we can deliver. So we are coming very close to the bare metal performance. That is our objective. Okay. And the other thing was we went more into this. I presented some of the things last year here. So what is happening is, since we are talking about big data, many times there is the interplay between network and also the storage devices. And when I say storage devices, like you might have some systems with only hard disks, or you can have a very fast SSDs, and the answers differ. Okay? Because SSD, many times what has happened is, like if you have a hard disk, that becomes the bottleneck. So even though you put very good performance networks, high performance networks, you will not see benefit. And that has been like some of the people have already indicated saying, no, I mean there are no benefits of high performance networks, because if I put, I don't see it runs same as 1 gig. But this is not the issue of the high performance networks. Here the end systems or the total systems we need to see. And I'll show some results. And especially like once you put some SSDs and other storage technologies, they're emerging, and that actually changes the landscape. And we'll see that if you put the SSDs together with high performance networks, this is where you get the best benefit in this kind of environments. So let me go through one of these designs one at a time, and then show some of the numbers. So first we'll start with HDFS, then we'll start with MapReduce and HBase individually. Like each one of these components, like HDFS running over IB, MapReduce running over IB, HBase running over IB. Then we'll try to do some combinations. Okay? So here I'll just present only, due to lack of time, only combining HDFS and HBase, but now we are also combining everything so that you can get some benefits from all these combinations, and then I'll go into the Memcached. So this is the design which we carried out. So if you see here like the applications and the HDFS, so obviously the Java sockets interface is already there. So what we did is we wanted to enable the high performance RDMA communication while supporting the traditional socket. So we didn't want to throw it away. So it's like you can configure it with an option saying I want to run it over RDMA, but you can also have the old path. So you can also run sockets, you can compare the performance. And here what we did is, especially those of you who are familiar with HDFS, what it basically does is it tries to write the data. It goes through some replication process, like with different replication factor. The default is 3. So you are copying the data to 3 nodes. And that is actually the network intensive part. And then the HDFS read is mostly node local. So what we tried to focus is that going through this HDFS write, so that is the part which we changed. And we basically took the JNI interface here, and this is where we plugged our design, which can directly run over IB first. And And there are two issues here. So we are just trying to do it in two phases. So first phase is just changing the network part. Okay, we are not even touching anything at the top, like how the HDFS architecture has been designed. So that is the second phase we'll be talking. It's like a chicken and egg. Unless you modify, like the upper level architecture has been designed with slower network in mind. Now, unless we accelerate the network part, then we cannot actually go to the upper part, and that's what we'll be doing in future. So today I'll be mostly focusing on the results, only changing the low level network part and no changes to the HDFS architecture. Okay. So this is the paper we had at SC in November. So that has all the details. So first, these results we are trying to show, just trying to reduce the communication time. Okay, not the total HDFS, just communication time. Here what we are trying to show, this is like different file size, like 2 gigabytes to 10 gigabytes. And here we are comparing with 1 gig IP over IB, and then this is the OSU IB design. So both are on the InfiniBand on the same QDR environment. So we have the same cluster connected with QDR, and we have the standard 1 gig as a backup. So we are taking the numbers on the same clusters just to have the equal benefits to all the other components. So here we have a 32 data nodes with hard disks, and here we see that as the data size is increasing, so here we are seeing around 30% improvement just in the communication time. So this is like the replication time, where it is going over 1 gig versus IP over IB versus the native design. And of course, with 1 gig, we have like 87% improvement. We didn't have enough 10 gig cards to put it on this cluster, but we are getting those numbers. So in the near future, you will see we'll show a complete comparison. That's the always people ask the question, okay, how about 10 gig? We have other cluster with 10 gig, I'll show some numbers, but we want to unify on the exactly same cluster. We can take the numbers. And so that is the communication time. Then the thing is, whenever people talk about Hadoop, there is a test DFS IO. So that is the kind of a standardized benchmark. Many of you might be familiar. So people try to find things saying not just at the lowest level, but can I really deliver the benefits at the test DFS IO? So we ran it here. So this has been run with 32 nodes with hard disk, and then 4 nodes with SSDs. And similar kind of trends we see. So this is like the throughput, so the higher is better. So here you can see this is the 1 gig, this is the IP over IB, then this is the native design. So here we see around like for 8 gigabytes, we see around like 13% benefit. It's running on the same thing. Instead of running over IP or IB, we are just running over the native IB first. And here on the right hand side with SSDs, we see around like a 15% benefit for 8 gigabyte file size. And then here what we did is, it's not just between the hard disk and the SSD, but it also depends on how many of such hard disks you are providing, how many of hard disk or how many of SSDs, because now you have more disk capacity. So here what we ran the experiment. So this is there are 6 lines here, so 6 bars. So the first 3 correspond to only 1 hard disk per node, and then the remaining the 3 ones correspond to 2 hard disks. Okay, so we wanted to see, okay, by adding more hard disk, are we getting real more benefits? And here we'll see that here we get around like 10% improvement over IB with around 10 gigabytes. But when we put like 2 hard disks, so here we see around like 16% improvement. Okay, so because like we are providing more hard disk than a lot of data. Now the earlier with 1 hard disk, it is getting choked. The IO subsystem is getting choked, so we don't see the benefits from the network. But now we increase that to 2 more hard disks, 2 hard disks, then we see even more benefits. Okay, and then if you compare like a 2 hard disk to 1 hard disk, we see like we get around like a 2 factor of 2 improvement for the native design, whereas for IP over IB it's around 1.8. IP over IB also shows benefits, but then the native design is giving even better benefit with 2 disks. So then we try to run a little bit going up. So there is a benchmark called YCSB, which is a Yahoo Cloud Service benchmarks, which is again a common benchmark people use. That's kind of a database or the HBase operation running on top of HDFS. So what we did is, it's just the first thing is the HDFS we changed to IB, but the HBase is still running with TCP/IP. Later on, I'll try to show the combined number. So we are just changing the HDFS IB, but then trying to ask the question that can the upper layers or other applications like HBase be benefited with this. And here we see like on the left hand side, these are like put latency, and the right hand sides are the put throughput. So here it's a lower is better, this is the higher is better. So here if you see around like a 480K HBase record, So here we see if we get the IP over IB, we get around 2.272 microseconds, whereas the native design gives around 201 microseconds. And similar kind of things here we see in terms of throughput. So broadly we see just by changing the HDFS layer to the native IB, even you get the benefits at the HBase layer, around 26% improvement in average latency and around 24% improvement in the throughput. So almost like 25%, 25% we are seeing the benefit. So that's the HDFS. Then we went ahead and looked at the MapReduce because that is also another significant component. A lot of people are trying to run the applications. So we broadly took a similar kind of design. So this diagram is very similar to the one we presented earlier. So what we did here is the RDMA-enabled MapReduce. Okay? So that means not only like in memory you are trying to perform the operations, but outside also these mappers and reducers, they are actually communicating with RDMA. And the same approach we tried to do, that we took the JNI interface, and this is our design which is running with IB verbs, and we still have the sockets, traditional sockets interface. Now here the common benchmark which is used on the MapReduce is called SORT, TeraSort, those kind of benchmarks are available. So here we started with the SORT. So the SORT size here is like 5 gigabytes to 20 gigabytes, and then also here we increased 25 gigabytes to 40 gigabytes. Now when trying to do these sorts, the amount of memory per node also matters, right? Because we are talking about like how much data can be in the memory versus how much we can go to the outside. So for the 5 to 20 gigabyte sort, we used around 4 node cluster, and then for higher data side we went ahead with a little bit larger cluster, like 8 node cluster, and here we had SSDs and we had hard disk, and broadly we see like in 15 gigabytes of short data. So you can see we get almost 46% improvement compared to IP over IB. So this is the GIGI, this is the IP over IB, so this is the drop you see. So by moving to the native design, we get around this much improvement. Yes?
Runtime or network time?
No, this is the runtime, total, short time. That's what we are showing, not just the communication time. Yes?
Is this broken down for mapping these spaces?
Not yet, not yet. No, not in this presentation, but we have the numbers. Okay. So then here we see like around 40 gigabytes of short, then similar kind of things. We see 27% improvement, like going from just the IP over IB design to the native design. So then we went into the TeraSort. Again, the TeraSort here is trying to keep on increasing the data size again, 30 gigabytes, 60 gigabytes, 100 and 200 gigabyte. And here again, we chose some appropriate systems. So the smaller scale ones, these machines had 24 gigabytes of RAM each. And then as we went into the larger size, our cluster didn't have more memory, so they have around 12 gigabytes of RAM. And all nodes have the single hard disk. So this kind of the contemporary systems people use. And here, for 100 gigabyte sort, again, we see around like 41% improvement over the IP over IB. So again, just by moving the MapReduce to the native IB level, we are able to give you benefits of 41% improvement. So then there is a new workload benchmark suite has come. The Purdue people, there is a group of researchers, they have pushed this as an open source called PUMA. Okay, so it says Purdue MapReduce benchmark. And it actually has different kinds of sets of benchmarks, like a representative set of benchmarks covering different application domains which people are using the MapReduce for. So for example, like adjacency list, self-join, word count has been there for many years, sequence count, or inverted index. So these are like small benchmarks. You can operate on large scale data. And here, we are just showing here the IP over IB versus the native InfiniBand. So here we see like the adjacency list, we get around like 46% improvement for 30 gigabytes. And then for 50 gigabytes, the sequence count, we get around 33%. Okay? Of course, the answers will vary because these are different kinds of benchmarks. And that's what we see also in the scientific computing and all. Different benchmarks will give you different kinds of benefits or different applications. Okay. So then we did like a HBase, again just HBase looking at it on a standalone. We tried to do some analysis here. This is some very detailed analysis. We have not done that with the MapReduce completely yet. So what it does is like the HBase, if you take like a 1 kilobyte put and 1 kilobyte get, we actually try to find out how much time is taking place in the client serialization, client processing, server serialization, server processing, communication preparation, and then communication. So in the top, we see these are the actual communication and communication preparation. And that is the time we are trying to optimize. So this shows like with a 1 gigi, this communication is so high. This is the IP over IP, 10 gigi, and then finally this is the native verb. So that's the part we are trying to reduce, and then we see the benefits. So here broadly we see like a factor of 6 improvement over 10 gigi for communication time, and then again for 1 kilobyte gate we also see similar kind of things, 6 times improvement. So again, the HBase-RDMA design is very similar to what we did for the other one. The similar picture I'm just trying to show. We provide the sockets interface, but take the JNI calls, and then that is the one where we put our RDMA-based design. And now if you go into more detailed results, so this is the HBase single server, multiple client. There are different modes to run these HBase benchmarks. So here in this study, we had like, so the black line is 1 gigi. Then we had, this is the IP over IP. The blue line is 10 gigi. And then this one is the red line is the RDMA design. So here we see like around 4 clients for get latency. We get around like 104 microseconds. 16 clients, we get around 296 microseconds. And this is the operations per second. This is the throughput. So here you will see that this red line is trying to give us the good benefits. And broadly, we see like around 16 clients over 10 gigi. Here we get around 27% improvement. Okay, so this is on the same cluster. Again, we had few 10 gigi cards, and then we were able to compare. So then on the HBase here, the same YCSB workload, but we had read-write workload, so that this is like the read latency, this is the write latency. So here especially we kept on increasing the number of clients up to 128. So we get around again 40%, 42% improvement here, and then around 40% improvement here. Okay, by moving the design from IP over IP to the RDMA. So then we wanted to see these are isolated each component. Then we tried to put them together, saying are we getting some combined effect? Okay, so what we tried to do is like we took the HDFS and HBase, put it together. So these bars, like we'll see 4 bars. So this is the latency, this is the throughput. So what we are showing is like this is the 1 gigi, this is IP over IP. But now here, this is the line, whereas we have the HDFS with IP, and the HBase is IP over IP. Whereas the last line where both are running over native InfiniBand, both HBase and HDFS are running. So obviously you'll see that this red line always gives the best performance here in the latency as well as throughput on this side. So here we get like for 360K records, we see around 37% improvement over IP. And then just beyond the HDFS, we get another 18% improvement. That's the combined effect we are trying to see when both are running over InfiniBand. So then we try to do similar kind of things also for the Memcached, and the Memcached here, this kind of the architecture. So what we try to do is, again, just like the previous one, the Hadoop applications or the applications layer we are not modifying. It's only the lower level networks layer we are modifying. The same thing here. But we also provided a flexibility so that the clients can be sockets client as well as RDMA clients. And then here we introduced a master thread. We introduced sockets worker thread. We also introduced verbs worker thread. So depending on which client is coming, if it's an RDMA client is coming, we'll link it with the verbs worker thread. And if it's the sockets is coming, then it can work with the sockets. And so that means the Memcached server can serve both the sockets and verbs clients simultaneously. And then these are the kind of evaluations we did with Memcached server and the Memcached client. So now if you take a look at some of the detailed numbers, so here again the similar kind of coloring here. This is like the 1 gigi. This is the IP over IP. This is the SDP. In this study we had some SDP evaluation also. This is the 10 gigi, and then this is the OSU design. And here we had 2 kinds of design. The blue one is the RC based, and here it is a UD based. So we explored both just like in the MPI and all, we have RC based or UD based. Here we explored both. And here we see like this was run in a little bit older cluster. So this is the DDR cluster, and then this side is the QDR cluster. So if you take the numbers like 4 bytes RC or UD, QDR we get around like a 4 microseconds. You can do a Memcached Get. up to 2 kilobytes. We do around like 8 microseconds. And here, especially since we evaluated with the 10 gig, here we see around like a factor of 4 improvements compared to the 10 gig for the DDR cluster. And then the Memcached is, so this is trying to show the other things, the transactions per second. And here you see there is a big jump in terms of like whatever these are the red and the blue are the native designs. And here we are able to, like just on 8 clients, we are also able to go almost like a 1.4 million transactions per second. And compared to all other technologies, you will see that they are very low here, whereas the native design is able to push it. And then we scale to like almost here 1,000 clients. And of course, these are the depending on the, because it's a multi-core cluster, up to 8 clients, we see some good benefits. And after that, it goes down, but it still remains around like a 600, 700 K transactions per second. Okay. And then we went a little bit up, trying to evaluate with some benchmarks. So there is a common benchmark called Olio, which is used in this domain. And the similar kind of things here we see, like the STP, IP over IB. This is the OSU RC design, and then the UD design. We also had a hybrid design, just like what we have done for our PGAS and all what I mentioned yesterday. So here we see, as the graph shows here, I mean, for the RC and UD, we are able to do it in a very small overhead. And here we see around like 4x times better for 8 clients. And here we are trying to show, like as the number of clients increases, the hybrid design is always like equal or better than the RC or the UD design, because we want to also keep the memory footprint low in these native designs. And then here I have a student who works at Yahoo. We collaborated with him, and he tried to convert the advertising kind of benchmarks to a workload, okay, for us, trying to see how it will perform in this kind of our design. So it is not the real end application, but we have taken generated a benchmark from that advertising workload and trying to see how it works. And here we see like almost, even just with 8 clients, we get almost like a 12 times better benefits for the IP over IB. And the hybrid design, again, performs very similar to the pure RC design. So with these, these are the kind of a first set of things what we have done just to show or illustrate saying the potential for the RDMA-based designs here, presented some initial designs, results are promising, and we are actually working on integrating these components. And we basically want to, just like we started the MPI work almost like 12 years back, and then we see how it has progressed. We believe that similar kind of things can be done in this domain for people to actually take advantage of RDMA-based designs for large-scale big data. And so might be in the near future, we are planning on actually making a release so that people can actually try it out on their workload, their things. So we also want to introduce, just like the MPI things, if you remember, OSU also introduced a set of benchmarks. We call it like OSU micro benchmarks for evaluating all different kind of MPI. So we'll also be introducing like a OSU Hadoop benchmark, okay? Because people are still using TerraShort and all these things. They don't know what is happening at the lowest layer. So our set of micro benchmarks will actually allow you to evaluate each of these components separately, like are we getting the best performance at the HDFS or MapReduce or HBase, and then only you can go to the upper layer. Otherwise, it remains like a black box for many people. So that's what I have here, and I'll be happy to take some quick questions, or if you want to go for lunch, that's fine, and then we can talk offline. There are a lot of questions. Okay, yes.
You had on that TerraSort bar chart, you had strange nonlinear behavior at 60 gigabyte. Was that clarified, TerraSort? There.
This one, yeah.
Right, nonlinear behaviors at 60.
Yeah, because here what is happening is like, I mean, the nonlinear you were saying from here to here?
Yeah, that at least it bottoms out the gains at the 60 compared to lower and higher.
Yeah, because here I see, you see these machines are also different, okay?
Oh, okay.
Okay, that's what I explained, because for larger size, we want to went into we wanted to go into reasonable larger scale nodes, but those nodes didn't have enough memory. Okay.
Okay.
So that's what I clarified. So here, these are running with 24 gigabytes of RAM in each node, whereas here, these two are running with 12 gigabytes of RAM in each node. Okay.
So your presentation is highlighting the benefits of RDMA. So it seems a little unfair to me that you are comparing it with 1 gigi, comparing 1 gigi with QDR 40 GB, where the hardware itself is highly powerful. And also say, for example, what would be more fair, right? So in my opinion, it would be more fair to show 40 gigi Ethernet, which Mellanox does support in their FDR cards, and show 40 gigi with QDR, and then try to show the RDMA benefit. And just one more point to highlight over here is that QDR with the 810B encoding would give a theoretical speed of 32 Gbps,
yes.
Whereas 40 gigi with a 66-bit encoding would give a theoretical speed of 36 Gbps. Now, if we compare those two, then highlighting RDMA versus non-RDMA may be a more fairer comparison.
No, I think you didn't get all the things. Okay, 1 gigi lines are there, but all my comparisons, I'm not referring to 1 gigi. I'm referring to the IP over IB versus RDMA. So the numbers are on the same QDR. Okay, we are running IP over IP stack, which is the sockets, versus the RDMA-based design. So we are doing over the same network.
Okay,
and
so
those are all the performance.
what you're asking me to do is compare not the 1 gigi, but compare the IP over IB versus the IB. Those two graphs you want me to compare.
That's exactly, and those are the performance benefits I always referred.
But then won't the IP over IB, that stack, won't that have some performance lag just because of the stack itself, the code path overhead?
Because that's what is the current Hadoop, and all are sockets based. So what we are saying is the IP over IB is the only way to run it on the currently in the high performance networks. Okay, so we are just taking it on the same network. Okay, so it is running over IP over IB versus we have gone the RDMA based design, and this is what we see the benefits.
Okay, got it.
We can always do the all other comparisons, 10 gigi, 40 gigi, and all, but that brings different technologies.
Got it.
So here on the exact same network, we are trying to compare the TCP/IP through IP over IB versus the native design.
Okay. Thank you.
Okay. Yes, might be Josh raised hand a little bit earlier.
Thanks. Hi, DK. Great talk. So I had a question about the number of hard disks in the systems for doing the Hadoop testing. I think you said you had either a single hard disk or two hard disks. I think it's often the case in Hadoop configurations that they're configured with one hard disk per core, and then there are map and reduce tasks run essentially one per core. And I'm wondering if that higher throughput mode would change the results that you have. I actually think it might make the interconnect look, the high performance interconnect look more important, but I'm just curious your own perspective.
Yeah, I mean, definitely. So here that's why exactly we want to push out this some version of the code benchmark so that people actually do studies, because I don't have access to all different configurations. So here in these things, memory is playing a role, hard disk is playing a role, number of cores is playing a role, the number of hard disks. So you can have different kinds of configurations and then see where the high performance network is helping or not helping.
So, one quick follow-up. Could you say how many map tasks you were running per node? So were you running one per core, which would sort of be overloading the single disk?
No, I think it was 2 or 4.
Okay.
I can double check. But we are not like overloading the things. Next to you.
So on the IP over IB connected datagram, probably datagram mode.
This is the, I think it's a connected, reliable connected mode, I think,
Okay.
not the unreliable.
And our plans to test maybe with our sockets?
Yeah, we have not done that. I mean, so we'll be happy to. I think we saw that talk, but we didn't see any number, Hadoop, but we can compare with our sockets and see how it works. Any other questions?
Thanks. And one small question. I could have been overlooked something, but in the end of your presentation, you mostly had better performance for RC over UD. If that's the case, do you have an opinion why that happened?
This the Memcached design?
Yeah, like that slide.
Which one?
The previous, even this one. So
okay.
Here, 1 megabytes per second for.
Yeah, I mean the thing is
RC
like
RC and 1.3 for
yes,
UD.
yes. So I don't know. I mean, see, the UD also has the reliability issues and all, right? Because UD doesn't have the reliability, so we need to provide the reliability on top of that. So that might be contributing things, but broadly they're very similar. Kind of. Yes. Because we have, like, if we are trying to run over UD, we need to handle the reliability also. Okay. No questions? Time for lunch?
Okay, thanks, Dr. Panda.
Thank you.